Okay, and maybe we can take it away. Dixant, how do you pronounce this? Patum?
It's ATM.
Paytm. And he's going to cover in particular a paper that was in iClear, and we'll send this out. You can check out other works of his here, and of course, talk to him directly on Discord, hopefully. Okay, and as always, multiple ways to join, multiple ways to ask questions. We'll collate them. Olga will collate them here. And heads up about next week, Shuang will speak. And that's it. Take it away, Dixant.
Okay, all right. Welcome everyone. So I'm Dixant Mittal, and today I'll be presenting our work on learning to search from demonstration sequences. So this is a joint work with Li Wei Kang and Professor Vincent Lee done at National University of Singapore. So the central question we are addressing in this work is how can an agent learn effective search and planning strategies when it has access to only a set of expert demonstrations. That is, there is no simulator, no environment interaction, just a few observed trajectories. Okay, so let me start by motivating the problem a bit. So we know that search and planning matters a lot for complex reasoning tasks. If you take problems such as reasoning in LLMs or let's say real world autonomous driving. So for these problems, it's essential that we uh, sort of look ahead about the consequence of our actions and evaluate them, and then take the best action possible at the current state. And the need for search and planning algorithms grows as the complexity of the problem grows. So a big challenge in these real world domains is that the data is limited. We don't have usually we don't have a accurate enough simulator that we can simulate the future outcomes of our actions. Or uh, we usually what we have is we have a set of demonstrations performed by some expert in how in solving that task. So for these tasks, uh, learning from this limited set of demonstration has three key challenges. One of them being So one of them being that because we it's a limited set of demonstrations, so the state space coverage is limited. We don't know what could happen, what are the all possible states in the world, and what happens when we take some action. And because of that, we we are not because we don't have the simulator as well, so we're not able to explore the outcomes of our action. And even if we start to learn some policy from that limited data set, uh, the inequities in our policy will start compounding in a long sequential uh, decision-making task. So let us look at how people have tried to solve these kind of problems. Common approach is to, let's say, represent, take a neural network and treat it as a function approximator, and then learn the policy directly from the state space. So here the neural network acts as a mapper that maps state to an action. The good thing about this approach is that this does not need any kind of knowing about the world dynamics. So you give it a state, it gives you an action. But in our specific case where the data is limited and there's no exploration, this kind of approach tends to overfit on the limited set of data that we provide. The second approach could be that, well, I have very limited data. So what if I learn the model, the world dynamics itself, and then I can use the world dynamics to simulate the effect of my action, and then I can come up with the best action that I can take at the current state. This kind of approach works really well if the world model is simpler than learning learning the policy. So for those problems where learning the world model is simpler than learning the policy, this approach can give you good results if you have limited data. But usually what we have seen is that model-free approaches tend to work better than model-based approach if you start getting more and more data. The primary reason being that when we are learning the world model, there will be some inaccuracies in our predictions. And then when we use that inaccurate world model for planning, let's say a long horizon planning, then those errors will start compounding at each step. So there was a new kind of approach that became quite popular a few years back. That was that we take that we will not use a generic neural network architecture. Instead, what we will do is we will split our network into different components and then have some algorithmic structure inside the network. So those components, individual components, they behave as subroutines in the algorithm. And then we will give it a state, and then it will give us a policy or a queue function as the output. So popular methods based on this approach includes VIN, Predictron, TQN, I2N, MGTS nets. In this work, we particularly looked at the TQN network. So what it does is it's a network that performs, it's a neural network architecture that performs a full tree expansion up to a fixed depth. And then uh, it tries to predict the Q value at the root node. So how it does that is it takes the input state, convert that to a latent representation using an encoder. Then it expands the tree fully up to a fixed depth into the in that latent state. And while doing so, it predicts the reward for each action that it takes and the value of the leaf nodes after the full tree expansion. So once the tree has been expanded to a predefined depth, then comes the backup phase where it starts from the leaf node and starts updating the, the value estimates of the the interior tree nodes based on the children estimates. And by following this method, it outputs the Q value at the root node for all the actions that are possible at the root node. Okay, so talking about the strengths of this method is that it has a strong inductive bias of a full tree search algorithm, and since everything is done in the latent space, there is no dependency on the simulator. So it it learns the world model and the planning algorithm all jointly in an end-to-end fashion. But it also comes with its own set of limitations, namely that because TreeQN is performing a full tree expansion, so the size of the tree grows exponentially in the depth. And because of this limitation, it becomes very hard to apply this method on complex reasoning problems where we may need to reason for multiple steps in the future. So based on this idea, we came up with differentiable tree search network, where we're replacing the full tree search algorithm with a best first tree search algorithm, where the tree is expanded in tree is expanded in the latent space in the most promising areas. And let me first give an introduction of D-TSN. So D-TSN is a modular neural network architecture that comprises of several parametric submodules which are learnable. It has a strong inductive bias of best first tree search algorithm, which allows it to scale to even more complex problems because it doesn't depend on the size doesn't grow exponentially with the depth. Further, it uses a learned world model so that there's no dependency on knowing a simulator to perform the search. And it does a joint optimization of all the submodules in an end-to-end fashion. Then there are some technical details that I'll talk about at the end of the talk, like how we made this work, and what are the challenges that one might face. Okay, talking about the submodules of D-TSN. So it consists of four submodules, namely the encoder submodule. There's a transition module, then there's a reward module, and lastly, there's a value module. So each of them, as the name suggests, they encode the input into a latent space. Then the transition module essentially predicts the next state's latent encoding. The reward module will predict the reward that we will get if we take that action, and the value module will predict the value of any state in the tree. Okay, so let's see an example how D-TSN works in practice. So we start with a latent state representation. Oh, sorry, the input state here on the left hand side. It passes through the encoder network, and it gets converted into a latent state H naught. Then H naught becomes the root of our search tree. Then what we do is we go into the expansion phase where we will iteratively select uh, a leaf node, and we will expand that using the transition module. So the transition module, it takes the parent's latent encoding and the actions that can be performed at that state, and it gives us the corresponding latent encodings of the next state. The reward module will take uh, the the encoding of the parent, the latent encoding of the parent, and will provide us with the reward for each of the actions that we can take at that state. And then the value module will take in the leaf nodes encoding, and then it will output the value estimate of those children nodes. So this is an interesting part here. Like since once we have a tree, a partial tree here, then how do we select which node to expand further? So what we do here is we compute something called the path value, where we say that okay, so if we start from the root node and we traverse till that leaf node, then what is the sum of rewards that we will get along that path plus the value of that child node. So that gives me the expected you can say expected value of the path from the root node to that leaf node. So once we have those path values, what we do is uh, we apply a softmax operation on them, on the values, and then we sample a node from that uh, from that so first of all, we define a tree expansion policy by applying the softmax operation on the path values, and then we sample a leaf to expand from that expansion policy. So let's say here H2 gets sampled, and then I will expand the H2 in a similar way I expanded H0. I will pass H2's encoding via the transition module, which will give me H3 and H4. Then I will get the corresponding reward values and the value estimates. And then I will repeat the same process again until my search budget is exhausted. Let's say I had defined a budget that I will expand up to 100 nodes. So once I expanded the 100 times, then I will stop. Okay. So let's say this is my partially sampled tree after 3 trials, 3 expansion steps. Then my expansion phase is over, and then my backup phase start, where I will recursively apply the Bellman equation on all the interior tree nodes based on the value estimate of their children. So I will apply compute the updated value of h3, I will apply a max operation over the value of its children. Then going one step up, we'll compute the value of h2 by applying a max over its children, and so on. So by doing this operation recursively, uh, I will what I will get at the root node is the path that corresponds to the best value at each of the action at the root node. For example, for the left action at the h naught, this was the best path, and similarly for the right action, this may have been the best path at the root node. Okay, so this becomes the output uh, of my network. So this is the output Q values that I will use uh, for downstream tasks. Okay, let us also have a look like what is happening in the background when we were uh, doing the expansion and backup phase. How was the computation graph being made in the backend? So we started with the input state, which gave us h naught. Then we chose one action, and we used the transition module, which gave us the next latent encoding. Then we passed it through the value network to get the value estimate. And we also passed the h naught via the reward module to get the reward estimate. And then we combine them together to get the value estimate of at the root node, the Q value estimate at the root node of the left action. Now, what I can do is I can use this uh, Q value estimate at the root node, which is parameterized by all these parametric submodules, and I can compare this Q value against a loss function. And when I compare it against the loss function, I can, because the whole operation is differentiable, I can compute the gradient of the loss function, and then I can backpropagate the gradient through the whole network. So it will update my value, the parameters of the value network, the transition network, the reward network, and the encoder network. So in this way, I update my network directly from the Q value estimate uh, through all the submodules. Okay, so let's have a quick comparison with TreeQN, how D-TSN is different from TreeQN. So remember, TreeQN was doing a full tree expansion from the root node. So the size of the tree becomes exponential in depth. And if you have, let's say, a lot of actions, then you can't really go maybe two-step deep. Whereas in D-TSN, because we are only expanding one node at a time, so you can go much deeper based on how much budget you have. Okay, so now comes the tricky part about the D-TSN. So we all know that for effective optimization using backpropagation, we must have the loss function to be continuous in the parameter space theta, so that we can apply the gradient descent algorithm, right? For methods such as TQN, which is expanding the full tree up to a fixed depth, the output Q value is continuous in the parameter space. But we cannot say the same about DTSN, because DTSN because the best first search that we're doing in DTSN is an approximation to the full tree search solution. So the Q value that we get at the root node actually depends on the tree that was sampled during the forward pass. And because of that, the loss function that we get that we will apply or at the output Q values may not be continuous in the parameter space. So how do we fix this thing now? So so what we did was, instead of optimizing the loss function directly, we optimized the expected loss value, expectation taken over all the all the trees that are possible, all the subtrees that are possible. Now, if you look at the if you look at this expected loss, and if you open it up, it comes out to be this value, and this can be shown that this value is continuous in the parameter space. Okay, so we fix that by replacing the loss function with the expected loss. But now, if you want to take the gradient of this loss function, it it turns out it turns into this long term where there are two parts essentially. The first part, if you look at the first part, this is the regular policy gradient term that we see in the reinforced algorithm, and this term corresponds to the tree expansion policy. So this term will optimizing this term will improve the tree expansion policy, and by improving the tree expansion policy, we are making our search more efficient. And the second term here is a regular loss function, is a regular gradient of the loss function that we apply on the Q output Q values. Okay, so those familiar with the reinforced algorithm also knows that the policy gradient term has as a issue of high variance. So what we can do here is, so if you look at this loss, this term in the formula, we can decompose this term as a telescopic sum by rearranging some terms. So if we assume L0 to be 0 and the loss at final tree to be this value, then we can say that okay, we can represent this loss as a telescopic sum of intermediate losses, difference between the intermediate losses. So what this let us do is, it lets us define the tree expansion as another decision-making problem, where the goal of the problem of the where the goal is to reduce the loss after each expansion. So now, if we define the for this problem, we define the reward as the difference between the two consecutive losses, and then the sum of rewards will become this value. So if you apply the reward at final step, it comes out to be the same value as in the original loss function. So we again look at our loss function, uh, the gradient of our loss function, and then we can replace this LT by RT by definition. And then, due to causality, we know that the future cannot, I mean, the loss of our future action does not depend on the past. So we can replace this reward by RT by R small t, right? And then we can replace this R small t by its definition, which is the difference between the final loss and the loss before that. Now this loss function itself has lower variance. So we did not choose to do further optimization tricks, but we can do a whole lot of tricks like having some GAE estimate and other stuff. But this term itself was enough for us to get a lower variance estimate of the loss function. Okay, so we tested For the experiments, we tested D-TSN against three comparable baselines. One of them was a model-free Q network, where we took a simple neural network of the same class as D-TSN, and we learned that network end to end without any algorithmic bias in it. For model-based search, what we did was we learned the world model and and the value estimate separately, and then we combined them using the best first tree search. So there was no joint optimization done in this process. And for the third baseline, we chose to go with the TreeQN, and we did all the joint optimization and full tree expansion in TreeQN. Okay, so we one of the domains that we chose was game of 24. It's a domain where uh, we're given some numbers and we have to apply some. So we are given some numbers and some operands, sorry, some operators, and we have to apply those operators on the numbers and get to the sum 24 at the end. So for this problem, the world model was quite simple. So we did not learn the world model in this problem. We just went ahead and used the world model directly. But the effect of learning how to search was clearly shown in the results. So we compared D-TSN with our baseline, which was we did SFT separately, and then we combined it with the online search, the same search as we did in the D-TSN. And the success rate of this method was lower than D-TSN across a range of demonstration. I mean, different number of demonstrations that we tested upon. Okay, the second domain that we tested this method on was Procgen. So Procgen is a set of procedurally generated environments where you don't get the same environment a second time you run it, and it is a set of 16 different games, and it is specifically designed to test the generalization capacity of agents policy. So it's different from Atari games in that aspect. And what we did for each of these games was we collected 1,000 trajectories using an expert policy for training, and then we saw how good was each method able to learn the policy from those 1,000 trajectories. Okay, so for comparison, we use z-score here. Uh, the baselines were again model-free Q network, model-based search without the joint optimization, TreeQN and D-TSN. And across the range of 16 games, D-TSN was the overall better method compared to the baselines in both mean and median scores. And the third domain that we chose was 2D navigation. And we specifically chose this domain to actually see what is happening and to visualize how good the planning is for each of the methods. So the scenario is quite simple. There's an inner hall and there's an outer hall. The agent starts from the inner hall, and there can be two exits or one exit in the inner hall, and the agent has to reach a goal position defined outside the inner hall. So what we did was we randomly selected the two exits in the inner hall, um, and random position for the agent to start at, along with a random goal, and then we showed it how to reach the goal by going through the openings. And here we did something different. What we did was we trained the agent on two exit scenario, but we tested the agent on a single exit scenario. So what we did was we trained the agent on a comparatively simpler problem, and we tested it on a much harder problem because of a single exit. Now the agent might have to take a significant detour before reaching its goal position. So to be able to find that exit, it has to plan. It sometimes has to have to plan to go away from the goal before coming towards the goal. And we saw surprising drop in performances for both model free Q network and TQN when we trained them on two exit scenario and tested on one exit scenario, indicating that these two methods were not able to uh, leverage the. I mean, model free Q network did not have any planning search structure into it, but TQN was not able to leverage the tree structure that it had because of the limited depth or the shallow search that it was performing to output the Q values. Whereas both model-based search and TQN, they were able to retain their performances. So, okay, to summarize now, D-TSN is a modular neural network architecture which has a strong algorithmic and inductive bias of a best first search tree search algorithm into it, which makes it more scalable than the let's say TQN. And for to do that best first research, it uses a learned world model to do everything inside the latent space, and then it jointly optimizes everything from reward estimate to value estimate and the world model, so that the whole search is optimized in a way to predict better q value estimate. That is the end goal of the network. And then we also saw that optimizing DTSN was not straightforward, and we had to come up with a lot of approximate loss approximations to make that happen. Okay, so that was my talk. I'm open for questions.
I don't know if anyone heard me, but thanks so much, Dixant. Nice talk. All right, Olga, speaking to questions.
Yes, thank you, Dishant, for the presentation. We have a few questions. First one, have you considered splitting perception and imagination into two concurrent tasks using a stigmatic memory?
Okay, so for me, what we were doing was that uh, the goal was to take the take the actual input as the network input and predict the final q value and do the whole search within the latent space. So we did not have a separate auxiliary loss for the perception part. We were optimizing the whole thing as a single process.
Mhm. Thank you. The next question is, where do the rewards come from and how are the values changing over time?
Okay, so the reward comes from the demonstration dataset that we talked about initially. So the demonstration dataset is a combination of, I mean, it's a so each sample is a tuple of the current state, the action taken, the next state observed, and the reward for that transition. So we call it a single sample, and then we have a trajectory of those samples that a sequence of that sample that becomes a trajectory.
Mhm. Okay, thank you. These are all the questions from the audience so far, but I do have a few questions from myself. So you compared your model versus TQN and some other models.
Right.
Uh, can you maybe summarize in a couple of sentences what is the key idea? What is the intuition? Why your model is working so much better than those ones? I mean, when you started your research, you probably looked at these other approaches, and you probably thought, oh, there is some issue that I would like to fix with this particular idea. What is this key idea? What is the intuition? How you did this so that it improved this performance?
Okay, so when I started looking at this work, so we first looked at TreeQN, and then we realized that what TreeQN is doing is not actually scalable for longer horizon task problem because of the limited depth that it can search to. So the question was that how can we have a better search algorithm that can do the similar thing but better, and it can scale to more complex reasoning. So we started from there, and then we played around with MCTS a bit, but then we realized that since we are learning the whole thing end to end, the best for search itself is enough, and we don't need to do MCTS or any other algorithm.
So it sounds like your approach worked better on problems with longer horizon, like more complex ones.
Right. Because that is the whole idea, that if we want to be able to scale our search to a longer horizon task, because uh, because when the problem starts getting more and more complex, you need to search deeper to be able to perform the actions better at the current state. And the real complexity in the current methods was that they were not able to scale beyond a certain point. They were either too simple. I mean, the algorithms that they were using, they were either too simple, or if they were using too complex algorithm, then they could only search to a small depth.
Okay, and then a related question is, what are the limitations on maybe the nature of the problem to which your method can be applied? I mean, for example, you learn world model, as far as I understand the way. So maybe there are some assumptions on how complex the world model can be so that you can efficiently run it. So is there some, I don't know, maybe formal description, or maybe at least intuitive, what is the nature of the problems that your method can be applied to? Probably it's not everything in the world, because world model can be too complex, right?
No, that is a valid question, uh, because what we are dealing with is a problem of limited data. So if the world model is too complex to be learned into, let's say, from that limited set of demonstration, then definitely that will also come into the performance. It will also affect the performance of D-TSN. But what we are doing is, let's say, if we are given a limited set of data, that this is all we have, now tell me how will you make my agent better from this limited set of data. Then we start to think about in that direction, then what are the possible options.
Okay, maybe last question from my end, and then Alex, I can pass it over to you.
Yeah.
So, Dixant, do you see some ways for future research, like what potentially can be done next? If someone gets interested in this work, what are the next steps could be? How it can be maybe extended to other problems, or I don't know, better improved further, or any other directions to get further from your work?
Oh, definitely. So one of them is you can say that it's reasoning in LLMs. We all know that the current LLMs are the reasoning in the current LLMs is mainly chain of thoughts reasoning. So they are outputting a long sequence of tokens, predicting, thinking about what the task says and how they're going to do their certain stuff, and then they finally output their what they want to do. So that chain of thoughts is a sequential process. They're not exploring multiple options at the same time. And the second limitation that we face with LLMs specifically is that they are predicting, or let's say the chain of thoughts is being done into the token space. So they have to come back and output something into the token space again for planning. But let's say if we were to be able to compress everything, my whole history on a prompt as an latent embedding, and then if I could perform the search within the latent search, I can look at multiple options and then choose the best one, and then directly output uh, my let's say the output of the LLM instead of having going through the whole chain of thoughts process. I can just look at my it's also similar to how humans we do. We're not thinking in terms of words. We're just planning of multiple things in our head together in parallel, and then we just output the best plan. Something similar. But the key challenge here that I observe is that the action space for current LLMs is vast. It's essentially equals to the dictionary size. So it's more than 100,000 tokens usually. So if I'm so when I'm doing the tree search and I have to look at 100,000 uh, steps at each at each state, then it becomes quite expensive to expand. So maybe some kind of hierarchical reasoning could come into play here, where uh, we are thinking about some sequence of tokens as one thought, and then another sequence of thought tokens as another thought, and then we are planning about them within the latent space, and then outputting the final answer. But yeah, but it's I mean it's just a thought. It is easier than I mean it's much difficult than saying it out.
Okay, great. Um, yeah, interesting work, Dixant. I like in particular that see we're overall trying to encourage more crossflow of ideas between neural and symbolic, and it seems to me a very kind of it's the in the on the neuro side, the understanding of search is, it could go a lot further, let's just say. So, and I think that's partly what you've done is kind of taken start to explore what further you can do on the search side. And because really we just have MCTS is what people know about kind of on the neuro side, Alpha Zero and so on, which is great, but not the only game in town, not the only idea around search that really is the heart of symbolic AI and a lot of other stuff that's been done in search. Um, so I'm just kind of with that kind of backdrop, one of the big ideas, for example, in search is the idea of viewing it as understanding a heuristic and things you can prove about different heuristics, and of course, and you have A star and so on. So can you say a little bit about your best first heuristic and kind of what properties you think it has, or what you could possibly do further with it?
Sure. So if you look at the way we are optimizing the network, so what we're doing is we are starting from the input state, and then we're expanding the tree, and my output depends on the tree that I expand. And within my loss function, I also define a term that is optimizing the tree structure that I form during the search, so that my value estimates improve. So in a way, I'm also optimizing the search itself.
Yeah, it is interesting. You sort of have two layers to it, right? And you said even tree expansion is itself a decision problem. So now, what do you think you can, or when you look at that as a general heuristic, you think is sort of a general pattern here that can be formalized?
I mean, so the way we look at the problem was that yeah, so we are not defining any heuristics ourselves. We're just going to let the network learn the heuristics by itself. Whichever heuristics let it output the Q values better, reduce the loss function at the prediction and the actual Q value. That is the best heuristics for that particular problem.
And one thing that presumably helps is the modularity. That and can you say more about what is the source of the modularity?
So the idea is that instead of having let's say a generic sequence of blocks after blocks of where the input comes from one side and the output comes out from another side, what if we divide the network module, the network parameters as a group of parameters? So each one is defined to do a certain task. So what ends up happening is that even though we have the same number of, let's say, 1 billion or something parameters, now the subset, because they have been divided into subsets, they have their own individual responsibilities. So in a way, what I'm doing is I'm reducing the space of hypothesis that my network can represent. If it were to be unconstrained layers after layer of agentic, I mean, sequence of network layers, then it can represent much higher number of hypotheses. But I'm forcing my network or the parameters to behave in a certain way that you have to fit my input and output mapping as well as follow this structure. So this is where my bias comes in, because it also comes from the knowledge about the problem. So since, let's say, if I know that my problem follows a certain structure about like what constitutes a good policy. Let's say if my policy is looking at the outcomes of different actions and then figuring out the best action out of them, then that structure is limiting the function that can fit my data, essentially.
And how important is that? Have you seen that be that sort of factorization?
Specifically, if we're talking about, let's say, data domains where data is limited, it helps a lot. In one of the experiments that we did, where we were on the navigation problem, where we trained on 2 exits and tested on 1 exit. So there we gave the same data to all the methods, but the generic neural network architecture with no specific structure was not able to generalize beyond a certain point. Whereas D-TSN, because it had that search uh, structure into its architecture, it learned that, okay, I should not go into walls and maybe I should plan my path around and look for an opening and then go through that opening.
And this is what you mean by a world model, right? This factorization.
Yes, the world model is a part of the network.
Okay, but is it actually that factorization that you mean, or something broader? When
So
you say,
essentially, what we
yeah,
so so what we did was we took our network and we split it into different parts, saying that a particular set of parameters, they are representing my world model, which takes in the current state and outputs the next state. And then, so those, the 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 responsibility, or the role of those network of the group of parameter was to represent the transition function as accurately as possible. So we did not have uh, a real simulator or a world model. We did not know about the world dynamics. We represented that using a parametric submodule.
Okay, so the transition function itself is your
Yeah.
robot. Are there any other things that appeared, Olga?
No, that's it.
Okay, great. Maybe we can put the link just on time. We can put the link in the internal chat for Dixant for Discord.
Oh, Dixant is already there.
Oh, okay.
Yeah.
Ah, thank you.
Thanks for having me.
Yeah, often it gets lost how to get to the Discord, where to go on Discord. So appreciate that. Okay, very nice results. I think very interesting viewpoint that can be built upon further. So encourage folks to look closely at this. All right, and in general, more thinking about search and learning heuristic functions. Thanks, Dixant. Really appreciate it, and thanks everyone for joining. See you on Discord if you have further thoughts.
Thank
Thank
you.
you all.
See you on next week.